All right, and then finally, what you're getting out of filling all the data into the audit software are a set of performance indicators. And as you will appreciate when you look at it, we don't have percent water loss anymore in there. The only time we're using percentages is when we're talking about financial indicators. But first, what I would look at, or I always look at when I look at a water balance, is the cost. So in this system here, it spits you out the annual cost of their apparent losses and the annual cost of their real losses. So, for example, their real losses cost them about $200,000. Their apparent losses $96,000, right? That's already quite informative. You get a good appreciation. So in dollar values, how much is it worth for what I'm losing out there? Next, what the software does, it looks then at operational performance indicators. And it's working towards normalizing those large volumes. So if you look at the top from the water balance, we've calculated for that system that they're losing 165 million gallons a year. Now, that doesn't mean anything to me. I mean, it's a large volume, but what is it? And how do you compare yourself against another utility with just this one volume? At this really great experience in a workshop a couple of weeks ago. So we had LADWP, Los Angeles Department of Water and Power, in the first row, and then next to them there was a small system that operates about 6,000 to 7,000 service connections, right? And so we're talking about how do we communicate our water loss performance and where we are. And the guys from LA said, well, you know, I know we should talk about volumes, but every time we use our volume, our leakage volume, people freak out because it's 1 billion gallons. And the guy next to LA said, well, sure, because it supplies my system for 3 years, right? That threw out the issue there with those big volumes, right? So I said, well, then let's use the software. Let's take a look. LA, how many service connections do you have? So they operate 700,000 service connections, and the other guy operates 6,000 service connections, right? So dividing 1 billion gallons by 700,000 service connections by 365 days, their real losses per connection per day are around 25 gallons per connection per day. So then I was asking the other guy, so where do you land? Like, well, I'm at 28. So now you can compare apples to apples, right? And that's the reason why we normalize those large volumes by dividing them by the number of service connections and the number of days you operate your system at. And that's also when you're looking across your boundaries, those are the numbers you should look at. You shouldn't look at what's your percentage or what's the total volume. It's really those normalized operational performance indicators.
It's also helpful if you're experiencing any growth and you're doing this year to year. If you install new infrastructure, you're also going to accumulate more leakage. Accounting for the fact that there's more infrastructure out there, by normalizing your leakage volume will let you think about how your system changes year to year without the confounding effect of growth. And the other thing we like to throw out there is that when you work with these performance indicators to someone uninitiated in water loss control, when you talk about losing 25 gallons per connection per day, they immediately jump to the fact that every single service connection is leaking 25 gallons per day. Oh my gosh. That's not actually what's going on. It's not as though there's 25 gallons coming out of every single service connection. It's just a way to take a big volume and scale it. And then lastly, for the wonks in the room, back it up for me here.
Sorry, I thought you were...
no worries. The infrastructure leakage index. This is a way for us to acknowledge in mathematical terms that all systems leak as one principle, and that there is a technical minimum volume of leakage that a system could achieve were it to employ all of the most aggressive leak monitoring and intervention and response strategies. The technical minimum is very rarely cost effective, so it's just a way for us to appreciate how we could perform if we needed to go that way. But generally between what is a technical minimum and where you are now is some sustainable threshold. And so the infrastructure leakage index is the ratio of your actual volume of leakage that you calculate with the water audit, those billion gallons for LADWP, compared to the calculated technical minimum. So it's a modeled figure working with your infrastructure. So when you report miles of mains and service connections, that is incorporated here, as well as your operating pressure. If you're gunning, 95 psi in your entire system, you're going to leak more just naturally than a system that runs at 60 psi. given that you'll have more leaks and you'll lose more water to every leak.
Before moving on, one more thing to look at. You see what is written up there in red. That seems to be important, right? Since it's in red. So what this is, it gives you the data validity score of your water audit. So depending on the grades that you have assigned to all of those volumes, then it calculates the composite data validity score for your results. And that can be between 0 and 100 is the highest. Nobody should be at 100 because, again, that would require so much work and effort in terms of making sure that the data is perfect that it doesn't make economic sense. But it gives you a real good appreciation of the quality and certainty of the data that informed your calculation. So if your overall data validity score is more on the lower end, that's perfect, that's great. Because actually you know that the first order of business is not to worry about those numbers in there, because right now they're on fairly shaky ground. I have sort of a general idea, but it could go up or down as I'm improving my data. So I'm really focusing on my data first, if I'm in a lower range of data validity score, before I'm even thinking about spending money on intervening against leakage losses or apparent losses. Does that make sense? Great. All right, next.
Other components of the software for your enjoyment, there's a visual results dashboard that displays your water volumes scaled. So this is the water balance just represented, where the biggest volumes represent the biggest space. And you can also see how the costs of different components of your water compare to one another. You can play around with that, have some fun with the visualization. That's in there if you need it. We've also got, in thinking about our performance indicators, I'll actually have you bump forward here, Chelsea.
Just one?
One would be great.
Okay.
We have not been talking about percentages quite intentionally. Up front, I acknowledge that percentages are an easy way to communicate when you're talking to an audience that perhaps doesn't have the same background or technical knowledge that you do. It's a way to bridge the divide there and to talk about terms that people are familiar with. But percentages can be misleading when used to track performance and to set targets. So in our Seussical example, we have the cities of Westville and Eastville. They sit next to each other, and by some stroke of magic, they're the exact same. They have the same infrastructure, they run the same pressure, and they have the same volume that they have to produce. So both Westville and Eastville input into their system 100 million gallons per day. They sell, in this 1 year, 80 million gallons per day. Therefore, their volume of non-revenue water is the difference. It's 20 million gallons per day. Right now, everybody's looking at system law of non-revenue water, 20%. All right, keep that in mind. Bump us forward, Chelsea. Eastville has a drought. This is where they are no longer the same. Their customers respond admirably. They're asked to conserve, and they do that. Thank you, customers. So now, Eastville has to produce 20 million gallons per day fewer than they used to have to. So their system input volume drops correspondingly from 100 to 80. Their sales have dropped 20 million gallons per day, so they're at 60. But because they still have the same infrastructure on the ground, they still have the same pipes, they still have the same meters, their non-revenue water volume doesn't really change. Non-revenue water, and particularly leakage, doesn't have much to do at all with what your customers are buying. It's much more about the physics and the infrastructure of your system. So their non-revenue water volume doesn't change. But in percentage terms, they are doing worse than they were before because the denominator has changed. They now lose 25% of their water, even though it's the exact same volume, and they haven't done anything for their performance to suffer. So this can go both ways, the percentage equation, but generally, as our customers are becoming more aware of efficiency and resources is important, and revenues are decreasing and sales volumes are decreasing or flatlining, it's important to consider terms that are not percentages so that you don't, on paper, look like you're doing worse.
I actually prefer the example that we had before where a brewery comes in and they need more water and then the percentage loss goes down. That's more appealing to me, but then I was sort of overridden by my colleagues here. But it's, again, like Lucy said, it really goes both ways, right? And that's again the misleading part of it. If you try to compare yourself against any other utility, it's really meaningless. Doesn't mean anything what their percentage is compared to your percentage. You personally, sure. I mean, but then again, it's really not the right indicator to use when you're communicating with the public and with your customers, because it doesn't tell anything about the efficiency of your system.
We think that communicating in dollar terms can often be insightful. I have yet to meet the reporter or the concerned member of the public who appreciates the infrastructure leakage index nearly as much as I do. But try out different things, particularly in your utility and communicating with your colleagues, with your boards. See what metrics land home and challenge yourself to avoid percentage terms. So of course, we can't just take away percentages and leave you floundering. We have to substitute something else. We've talked about normalized volumes of loss, both real loss and apparent loss. There is the infrastructure leakage index. It's that simple ratio between your actual loss and your calculated technical minimum. So if your infrastructure leakage index is 2, you lost in leakage twice the volume as your calculated technical minimum. Just accounts for the fact that all systems leak.
So does that concept make sense, that there is a technical minimum level of leakage for any distribution network? That we don't have zero leakage, right? And there's something that technically we cannot push it further. I mean, you all know when you lay a new pipe, right? The pressure test, you have some leakage allowance already there. So that's part of our infrastructure. There will always be leakage, and we try to acknowledge that to say, here are the minimum allowances in leakage for any given system, and that's driven by miles of mains, number of service connections. And then realizing, okay, well, this is where we theoretically could be. Actually, we're here. We're 3 times more than the technical minimum. And that's all that it's telling you. It doesn't mean that you should be at the technical minimum. Economics will dictate where you should be.
And over lunch, if anybody is particularly inclined to modeling, we're happy to talk about where this technical minimum calculation comes from. There's a lot of research behind it, so we can entertain that later. So when you're working with your audit, the performance indicators can be used as a gut check on your data. Presumably, you lost some volume of water and had other uses that were unbilled, so your non-revenue water volume should be greater than 0. That makes a lot of sense. Similarly, your real loss leakage volume should be greater than 0. We've seen the occasional case where somebody will report that their leakage losses were negative. I would love to meet that person who can produce water by distributing it. It would solve a lot of the world's problems, but can't be done, not yet. First principles of physics would suggest otherwise. So check that your volume of leakage is greater than 0. If it's not, some other balance of your inputs is off. Other things to consider, your infrastructure leakage index should be greater than 1, indicating you lost more than the technical minimum and not less than the technical minimum.
I think just want to throw out this as some research that we've done for the Water Research Foundation. So what we've done is we looked at all the water audits that have been submitted to those states that require utilities to submit standard AWA audits to them. That there's a number of states out there.
We worked with 5. It was California, Texas, the Delaware River Basin Commission, Georgia, and Tennessee.
So those guys have been at it for a while, regulatory requirements, and then we collected all of these audits and basically looked at very simple checks. Do the results make sense? And those weren't very complex checks. One was, if you're reporting negative losses, then most likely something is wrong with your data, right? We will agree on that. If you're reporting that you're performing better than what the technical minimum would be, most likely some issue with the data as well. So these kinds of spot checks, right? And what we found is that typically between 30, well, the states where you had statewide programs that provided technical assistance to do the audits and where there was a validation component to it, they did better. But for the rest, it was anywhere between 30 and 50% of the data that is submitted that didn't make sense. Just right now, as we in California, for example, received the first data set of close to 400 water audits that are required by the regulator, 50% of those audits don't make sense. So as you're producing your audits, as you're looking at it, really look at those checks, just from the get-go. The numbers that I'm using, the outcomes, do they make sense? Do they seem reasonable?
And auditing is retrospective, obviously. You're working with data from a year that's already happened. It may be that when you pull up your performance indicators, having filled out the software, and they don't make sense, you don't know where the problem is, and that's okay. It may be that for that particular year, the problem isn't diagnosable, it isn't fixable, but it's something to think about in future years when you work on the quality of your data. Start with the things that you have the most suspicion about, such that you can triage a little bit your analysis and make it make sense moving forward. So, data validity grading. Wonky way to say assessing your operational practices and how those affect your audit. It's a pretty understandable concept that when your inputs into the water audit are incorrect or uncertain, of course then your outputs will be incorrect or at least uncertain. And our water audit can be affected by very different kinds of errors and uncertainties. Right from the get-go, we've talked a lot about meters and the fact that they may not register with 100% accuracy. That's something to consider. We've also got databases. Things like billing databases and SCADA historians can be black boxes. There can be some summarizing or manipulating of data that happens a little bit behind the scenes that we can't quite get our hands on. That is a common source of error or uncertainty in our water audit. We've also got people. It just could be that somebody is doing their job to maintain the finances of the utility, but don't appreciate the water auditing methodology, and therefore give you data that isn't quite what you were looking for because their definition was different from yours. That happens. Estimation is also something to consider. That can introduce uncertainty or error into our audit. Just because we don't collect all of the data doesn't mean we can't fill out all of the software, but there will be some estimation in the process as a result. And then lastly, missing information. That happens. That's okay, but that does affect our results. So the process of data validation aims to do two things. First of all, find errors, and if we can find them, can we correct them? It may be that no correcting data exists. That's okay. We just want to document that. Data validation also communicates uncertainty. It's a chance to acknowledge that water auditing isn't a perfect process, and we want to acknowledge that the results are only as good as the data that supports them. Data validation can happen at one of three levels. There's some research being published this fall by the Water Research Foundation that elucidates this a little more, but you can perform data validation with different levels of rigor depending on what your goals are. If you just want a cursory check on your audit, that would be considered a level 1 validation, where you focus on really getting those data validity grades right and looking at your performance indicators for believability or feasibility. You can dig a little deeper into a level 2 validation where you really interrogate your databases and your raw data sources for that data story making sense and dig into the systems that produce your numbers. And then you can go to a level 3 if you are so inclined and work with field data collection and test your meters and do pilot leak detection to confirm your results of your audit and go out and pull customer meters and put them on a test bench and do some pressure logging. That would be a level 3 activity wherein you're taking what your databases produce and matching that up with what you understand about your instrument's performance. Data validation doesn't fix all the errors in data. It could be that you performed levels 1, 2, and 3 and you still got something funky. Because auditing is retrospective and you're working with archived and historical data, that can happen. But it's still a worthwhile undertaking because the more engaged you are with your data, the more likely it is to reflect your operational reality. We've talked about this. We just want to reinforce the fact that all criteria must be met for a score to apply. It could be that you correctly assess your data validity grades and then you go sit down with your general manager and he says, no, we're at 10 all the way through. I hope you'll come back to the perspective that all criteria must be met.
We actually had that in a workshop a couple of weeks ago, that there was one attendee in there, and she was saying, well, I've done this and I've used the guidance and assigned the appropriate data grades, and typically anywhere between 6 and 7, and that's what we're doing. And then I had the meeting with my general manager, and he said, we had 10. From everywhere 10. I said, well, that's what it is. This is also the value of sort of those third-party validation programs, right? Where then someone independently reviews, and then you can say, well, look, I mean, given the data that you've provided me, the backup information, you're only a 7, and that's perfectly fine.
In the software, mechanically, the data grading criteria are in 2 different places. One is when you hover over the box where you input the score, it gives you the rainbow text, nice cheerful text that allows you to step through from 0 or not applicable to 10, your scores. There's also a matrix, which when you pull it up, you'll want to print it on like a wall-sized piece of paper because the font is tiny. There's a lot of information there, but it's a great way to see everything in one place. So we're going to walk through an example. Go for it, Reinhard. Start us off.
All right. So what we'd like to do is just to give you typical scenarios that we encounter when folks bring their data to workshops or when we engage with a utility, describing the current situations of a utility and what are the questions to be asked. So first on the sources, do you own, are you all the own sources metered? That's the first question. Do we really meter everything, right? And what about calibration? So do we do calibration or don't we do calibration? We heard before a lot of folks do calibration. Do we have documentation to support the claim that we calibrate? There might be someone out there saying, yeah, sure, well, we calibrate every year. And then you ask, can we see the data, the calibration certificates? And they might, it was the plan to do that, and 3 years ago we actually did it, but then something else came to the forefront as a priority, and now we dropped it. We're not doing it anymore. How often are we calibrating it, and what's the most recent results that we have for calibrations? In case you do more than calibration, are you doing any volumetric testing or comparative testing, so true meter testing? And again, in the same vein, asking, can I see the test results? When was the most recent one done? Does it apply to our audit period? So those would be the things when you're going through the first validity score review that you're looking at. And those volumes now, this one summary volume that I'm having here, the underlying data from my SCADA that comes in at a much higher frequency than just one annual number. Who is reviewing that? Have we had any lightning strikes happening that our SCADA was down for a couple of hours? Did someone fill in the gaps there, or do we have zeros? And when we pull down the cell and summarize everything, we're summarizing also the zeros where actually we still continue producing water. So those are the things you want to look at and ask questions around.
So in our example utility, they meter all of the water that they produce, all of the potable water at the effluent of their treatment plant. They do calibrate annually, and recent results have indicated that their signals haven't wandered more than 1%. So the calibrations indicate that their meters are trustworthy. They do not conduct any volumetric or comparative testing. They don't draw down a reservoir and compare how that volume looks against the meter register. They don't stick an insertion meter in the pipe and compare that to their meter. They also review production volumes monthly, looking at SCADA, looking at meter reads, and truing everything out. Given this circumstance, we now want to put them onto the data validity scale for the volume from known sources. So, for a score of 6, the definition is that at least 75% of treated water sources are metered. They meet that. They're at 100%. Meter accuracy testing and or electronic calibration of related instrumentation is conducted annually. That and or is helpful. They calibrate annually all of their meters. Sounds good. They satisfy the and or criteria. Less than 25% of their meters fall outside of a band of plus or minus 6% inaccuracy. Their results have been in the 1% range recently. Looks good. They exceed the criteria for a score of 6. The audit software is generally even scores, so we now bump up to an 8. And it says 100% of treated water production sources are metered. Still good there. Next, accuracy testing and calibration of all instruments is conducted annually. That doesn't happen for them. They just calibrate. They don't volumetrically test. So that's not true. And then there's still a stipulation that their meters fall inside a narrow band of accuracy. So they meet some of the criteria for an 8, but not all. And given our philosophy of meet, exceed, or retreat, we're going to retreat from a score of 8 to a 7, wherein the definition is, quite literally, conditions between a 6 and an 8. We were good for a 6, but not all the way there for an 8, so we bump back to a 7. And you'll do that sort of evaluative process of your practices for all 20 data inputs into the water audit software. So you'll have to also think about, when you come up with an operating budget, is it reviewed by a CPA? Is it comprehensive? Does it include sewer costs that you had to pull out? Those sorts of questions. When you talk about pressure, how many pressure zones are you operating? Are they discrete? Do you log pressure? Do you work with hydraulic model? These are the sorts of questions that you'll want to engage with your colleagues. And I'll also throw out that this fall/winter, the Water Research Foundation will be publishing a guidance manual to the process of level 1 data validation, which is in large part the process of selecting data validity grades. So these questions that relate to practices will be elucidated, drawn out in that manual.
But I think also to appreciate here, right, the requirements to meet a data validity grade of 8 that you calibrate and test. For some utilities, that might not be attainable, given installation conditions of the meters, that there's just no way of testing the meter. All I can do is calibrate the meter, but I cannot test it unless I go into some capital projects and dig up downstream and put a comparative meter then in there or a tap or whatever. So those are the realities. It doesn't mean because you don't meet an 8 that's a bad thing. It's just reflecting where you are. I mean, you can then evaluate, is it worth the money to get an 8? So the grades are simply there to sort of try, so how do I get the perfect grades? That's not the purpose of assigning data grades. We are certainly past the school kind of thinking. We don't need perfect grades. We just need grades that are really reflecting our operations and our conditions.
Of course, even though we say there is no perfect score, people still bait us and say, well, yeah, but what's a good score? Help me out. I acknowledge that you want a good score. And so the philosophy, of course, is that the good score is the one that is transparent and honest. But there are scores that indicate that data is more insightful and is usable for thinking about water losses and intervening against them. So generally the guidance is that when you've got a score above 50, ranging into 60, 70, 80, your data is good enough for you to start thinking about water loss control. The volumes that your audit's spitting out likely do reflect, with some margin of error, your system's performance. Below a 50 on the scale of 100, you might want to think about your data before you think about leak detection. But when you start to reach the upper bands, you won't want to pursue pilot studies or intervene, while at the same time keeping an eye on your data and making it more accurate wherever you're able.
Yeah.
If you have a low score, bump it up before you start digging up infrastructure or replacing customer meters. If you are very excited about the topic of data validity and do want to improve your scores, there are a few simple things you can do. One is test your instruments, whether that's customer meters or your production meters. Those will all increase your scores. Another is to investigate how well your data chain translates volumes from your meter to your 4 to 20 milliamp signal, to your SCADA database, to the historian, to the query that pulls it out of the historian, to the summary function that puts it into your Excel document. There's a lot of stuff that's going on in that data chain process. And if you can investigate from start to finish how that translates your volumes, whether that's a process of fidelity or not, that's helpful for increasing your data rates.
There's a great example that I've come across recently with a client. They replaced an old production meter with a new mag meter, nice installation condition, everything worked well. The only thing that went wrong, and that was only discovered by doing a comparative test, is that the scaling of that meter for the 4 to 20 milliamp signal was different than from the old meter, and that didn't change the scaling. So now all of a sudden that meter was under reading 20%, I mean just the data coming out of it through the scaling going from the 4 to 20 milliamp through the PLC and then the SCADA system. When you test it, you see it's accurate, right? But the data transfer is wrong.
Mm-hmm. We've also found that this is important in billing processes. It could be that if you operate a raw or a reclaimed water system, you keep all of those bills in one place, and the query you have programmed to summarize your consumption or your sales volume includes non-potable water, and you don't realize that until you dig a little deeper into what is actually going into that query in that script. So something to think about. Another is third-party review. When you get to the higher levels of data validity, the 8s, the 9s, they start requiring that you bring in outside expertise, whether that is a CPA for your financial statements or water auditing experts for your other cost figures. Next up, if you're doing things manually, the audit software recommends to improve data validity that you transfer to electronic management. I would also like to say that that is a huge can of worms, and it could be sometimes that walking over to your meter with a piece of paper and writing down the totalizer on the register, that works. So take it with a grain of salt that at higher levels there may be a slight divergence in questions of validity or operational practices and accuracy. The practices that are accurate for your utility may not map exactly onto general criteria. So this is a guideline, it's a map, it's a way to start conversations, but it's not the be-all, end-all when it comes to accuracy and maintaining your data streams. And then lastly, track estimates of unmetered use. That's a big one. That's important. There is a default in the audit software for things like unbilled, unmetered consumption, where it just says, takes a bulk percent of your supply volume and says, okay, that's your unbilled, unmetered use, things like operational use and firefighting. But if you have the chance to think about your flushing program and, take pressure at a hydrant and consider flow rate and the time you're doing it, just back of the envelope in a spreadsheet calculate those sort of things, it'll make your audit better. So we've done a water balance. We've used the AWWA free water audit software to account for our volumes. We know our volume of apparent loss. We know our volume of real loss. We have a suite of performance indicators that helps us to appreciate how we're doing. We have a data validity score that speaks to our practices and our data's quality. But we don't yet have enough to design a water loss control program. So to dig a little deeper, it's important for us to appreciate the types of leakage that happen in our system. Not all leaks are the same, and therefore to address them, you need a toolbox rather than a single activity. It's important to think about the costs of our leakage, what it would cost to go after it compared to how much it's worth. If you would lose money pursuing your leakage volume, it might not be worth doing. So we need a little more information to get to the water loss control level. It says afternoon topics. We're going to do it now before lunch, and then we'll talk more about the details of intervention this afternoon.
All right. Why component analysis? First of all, so I can repeat that word many times. But as I said to you before, the water balance, when you're done with it, you have one big volume of real losses, right? We already know that not all of that volume of real losses is technically recoverable, right? A certain component of that volume of real losses is just our technical minimum. And so in between the technical minimum and where we are now, there's a certain volume that is recoverable, but we need to have a deeper understanding of the subcomponents of our real losses, of our leakage losses, to really design the right strategy. Is leak detection what we need to do? Is pressure management what we need to do? Can we actually save some water by just repairing leaks a little faster than we know about already? So those are the things to think about. And there's not just one, I would say, one strategy that takes care of everything. Managing your leakage losses, it combines different components of those strategies that optimize how you drive it down and maintain it there.
Out of curiosity, does anybody in this room have a proactive leak detection program? Great. So we got some folks out there sounding for leaks. Be curious to hear a little bit more about that later.
Another question, who has done a component analysis?
Or a component analysis, either. No, nobody.
Nobody, okay. So, then that's great, that's timely, because also, I mean, typically, what's the basis for your leak detection programs? How did you come up with how much should it do every year in surveying the system?
We just do it annually because there was enough found when we were doing it every 2 or 3 years that we thought it made sense.
Okay, so you're finding enough every year, so you're surveying the entire system?
It's getting less and less.
Okay, interesting. How about you guys?
We hire an outside firm to come do leak detection
Every year, also the entire system? Oh, okay. So that's an interesting case. So this tool, this component analysis should actually allow us to put numbers behind it, to review, it's once a year the right strategy for you guys, or are you actually leaving some money on the table because there's more to be recovered, or can you ease off a little bit and don't do it every year, but do it every 2 years and so on. So that's something that this tool that we've developed will help you figure out. But going back to it and zooming out a little bit, as I said before, in order to get to what we call the economic level of leakage, so that's the optimum level of leakage or volume of leakage for your system given the valuation of your leakage. So if your water is more expensive than your neighboring utility's water, then you have a clear incentive to actually be more aggressive about your leakage losses, right? To survey more often. And that dictates how far should you squeeze that box of leakage losses. That's the outer box, the current annual real losses. Typically, we have three tools that are sort of short to medium term tools. Leak detection, we all know about that. We can go out and try that. Pressure management, a topic that I'm super excited about, but sometimes really, really hard to get folks also to share the excitement with me. And then repair time. So when you are aware of a leak, how long does it take to repair the leak from the time you're aware of it? And the combination of those tools will then get you to the economic optimum. But bear in mind, the inner rectangle there, that's the technical minimum. We cannot squeeze it any further than that. So somewhere in between, that's our optimum point.
We do want to match the tool to the type of leakage. For example, if most of our leaks are hidden, we haven't yet found them, is improving our leak response time once we know about a leak very effective? Not particularly. We don't even know the leaks are there to begin with. Simultaneously, if most of our leakage occurs as small seeps and drips at fittings and at valves and that sort of thing, is leak detection going to uncover that? No. So we want to figure out what forms of leakage we have so that we can pick the appropriate tools.
All right, so there is another software tool out there. Again, we call it a software, but at the end of the day, it's a spreadsheet, an Excel spreadsheet that we've developed for the Water Research Foundation. It's freely available. Everybody can download it and work with it. A little bit of a heads up, it's certainly more involved than putting the audit together. So in the audit software, you have 18 data entry points. In this model, you have many, many more, and you also need much more data. But anyway, it allows you to break your real loss volumes down into its subcomponents. And let's go to the next slide. Let's hopefully show you. So this is giving you the picture of your total real losses are made up by those three subcomponents. Let's start with those, the one subcomponent that everybody is aware of, the reported leakage, right? That's the leak, those leaks that come to the surface that are called in, they find you. You don't have to try and find those leaks. Some of them are in a more catastrophic fashion. Some of them are smaller. Your customer calling in, my pressure dropped, something is wrong on my service. But you don't go after those leaks trying to find them. They come to your awareness, right? Now let's look what we can do about reported leakage. Top, pressure reduction. We can do some replacement of mains and service connections to reduce it, but that's awfully expensive just for reduction of leakage losses. And we can look at the repair times. You know, for those leaks that are being called in, on average, how long does it take us to repair those? Now, since we have a couple of utilities in here that do proactive leak detection, you'll also have a database of all the unreported leakage that you're finding, right? So you have repair records. Okay, this year, by doing leak detection, we found 50 service connection leaks and a couple of main leaks, for example, right? So that's the volume we can then attribute to unreported leakage. The ones that are reported that find you, that's the volume that goes to the right. Ones that we find proactively, we categorize as unreported leakage. Also here, pressure management is a tool, and again, obviously, how long does it take to repair it, right? And that's a capacity question. And then finally, well, what is a little bit more of an esoteric kind of component is what we call background leakage. And that's all the small seeps and drips at joints and fittings. So everybody out there digging up the network, you see these drips happen, right? And they happen all over the system. One thing that categorizes those volumes is that by doing leak detection, you cannot find those background leaks because they just do not generate enough sound. So the way we find leaks is through the sound that the leaks are generating, right? Our system is pressurized, and once we have a compromise to our system, let's say a small pinhole, right? Water flows out, and the energy from the pressurized water is dissipated and generates a sound. So when I'm listening to a service connection and there's a leak, I can actually hear that sound, right? That's how we find leaks. But those background leaks, they just don't generate enough sound. I mean, the dripping, you cannot pick that up. Our instrumentation is not refined enough to do that. So what do we do about background leakage? One of the most effective ways is to reduce your system pressure, because that's going to really drive down these little seeps and drips, because they start dripping slower, right? So those are the three components of our total leakage up there. And as you see, you have to go after them and intervene against them with different strategies.
Is the wait and see strategy?
The wait and see?
That's right, because you know,
Yeah.
digging stuff up is too costly. Eventually, it's going to show itself.
Yeah, I mean, not that I heard that the first time. Yes, so some folks say, well, you know, if it's not big enough, I'm not going to dig up. The other argument there to be made is you never know what could happen to that leak when it turns into a more of a catastrophic failure, right? I mean, typically what we see when we really look at data, the cost to interact with your leaks is lower when you find them before they turn into bigger events. So there's something to be said, and you can schedule it, right? You find a leak through corrective work. You don't have to respond to it in an emergency fashion. You can actually say, okay, 2 days down the road, we're going to fix that, right? You don't have to sort of go into emergency response.
The other thing is that leak detection doesn't actually create leaks. They do already exist. And so getting to them sooner saves you both water and perhaps the liability of dealing with it when it is bigger. So though it may seem like an initial upfront cost to attend to leakage that's already happening, it's already happening. You just know about it. And in this case, knowledge is empowering. So when we think about our volumes of leakage, background is generally a modeled volume of leakage, given your pressure, given your infrastructure and its condition. We do have some allocations for those leak volumes. This is often surprisingly a bigger volume than people would expect it to be. Sometimes on the order of half of your leakage occurs as little seeps in terms of its volume. So something to think about and to acknowledge that that happens, and to attend to it, you have to think about pressure and infrastructure replacement. Other strategies won't attend to it. Conversely, working on it. The volume of reported leakage, the stuff that finds you, is usually, barring polar vortices, a surprisingly small volume of your total leakage, sometimes on the order of 10% of what's actually going on in your system. So you're probably interacting with much less leakage out of the total picture than you think you are. Just something to think about. Of course, you won't know that until you do the analysis for your own system, but that's a typical scenario. It's often visible leakage in California. They're detecting leakage right now with satellites. Where grass is green, they think there's a leak. They're going to find it. So there are a lot of different ways that this sort of leakage can make itself known. Customers or your staff seeing stuff while they're out reading meters, but generally a smaller slice of the pie. And then lastly is that sweet spot of unreported leakage. When you think about reclaiming unreported leakage, the question is, at what frequency should I detect leaks in order for this to be a cost-effective proposal? Most folks who have never done a proactive leak detection program will, in their first sweep, find a ton of leakage because it's accumulated over 30, 40, 50 years in their system, and there's a lot on the table to be recovered. Once you've cleared your system of that backlog of leakage, the question then is, what frequency do I have to survey to combat the occurrence of new leakage? If your system is old and has suffered some very harsh winters, perhaps your frequency needs to be higher because it's accumulating leakage more quickly. If it's a new system and it was installed perfectly, perhaps you have to detect less frequently because leakage is slow to evolve in your system.
That's exactly what you guys are talking to, right? I mean, you go there out every year and you still find leaks. So that's just what's happening in a system. A system is aging and new leaks develop over time. The only thing that if you're not proactively interacting with it, then a backlog builds up. And that's what Lucy said before. So when you haven't done leak detection before and you do it the first time, you probably find much more than what you find then in the subsequent years. Does that reflect your experience?
Yes.
Great. Next. All right, so this is an interesting example. That's the result of a component analysis for a system that's actually that was in Texas.
This one?
Yeah.
Yeah.
The breakdown here, you see out of the total volume of real losses, 45% is background leakage. So 45% of the total real losses or leakage losses, they cannot even interact with by doing leak detection, because it's those small seeps and drips. Do you remember what is effective to interact with background leakage? Pressure. Right. Okay. So 45% of that, if we want to do something about it, probably most effective to look at pressure reduction. Now, 15% of the total leakage volume or real losses comes from reported failures. So the leaks that came to the surface that they fixed. This is calculated based on how many events did they attend to, how long did it run for, what was the average flow rate. Nothing complicated or magic about it. And what is left over then is unreported leakage, right? The green part of it. Now, here's an interesting thing that you get out of doing this type of analysis. So the total volume of unreported leakage, 11% of that was actually recovered by their leak detection program. So they hire a company, or back then they hired a company to survey, I think it was 30% of their system each year. And so we had the data from those surveys for that year, how much they found and how much leakage they recovered by doing that. Now, when we were done with this analysis and I looked at it and I said, well, you're surveying 30% of your system, but you're not recovering 30% of the unreported leakage out there. Something doesn't match, right? You would actually think you find more than just the 11% because they're covering 30% of their system. So then we went back to reviewing what they're doing, and it was a function of how the survey was done because they were just going from valves to hydrants and not really listening to the service connection, so that they were missing a lot of the leaks. And that then informed the decision. Well, we're going to tender again and figure out that we get a survey that is very detailed, because if we're surveying 30% of our system, we want to recover leakage in a similar magnitude to that. Does that make sense?
And that sort of thing, if you see a scenario wherein what you're doing isn't mapping onto the results you'd like in terms of leak detection, it could also be a function of geography. It could be that the parts of the system that they're surveying more frequently aren't the parts that are leaking more frequently. And that sort of information you can gather with multiple phases of leak detection, but also with sectorizing your system. And as we talk about advanced management for water loss control, that'll come up, this concept of district metered areas, or discrete zones, wherein you can create a water balance on a smaller scale, a little bit more localized, so that when you go out to do leak detection, you don't have to do your whole system all the time in order to get your leaks. You can actually pinpoint them in their location a little bit more exactly and attend to them faster. So if you want to work with the component analysis model, it is available free through the Water Research Foundation. The project number is 4372A. There's both the software, Excel tool, and a manual on how to use it. We're also happy to answer any questions you may have as you're working with that. Just shoot us an email. As the research folks, that gets us excited to talk with folks about what we've done. So to get to a water loss control program, we've done our water audit, we've done our component analysis to design our leakage profile. And now the question is, what's cost effective in terms of addressing our losses?
So also to repeat again, I mean, I would certainly commend you guys for doing what you're doing, that you're proactively going out there and you're still finding enough. This tool gives you an opportunity to review is, the annual survey, the correct frequency, or should you actually do more than that or less than that, given economic terms. Because once you have this breakdown of your leakage losses, the next step then obviously is the economics. That's also part of this software tool that you can then determine the right frequency.
The component analysis is based on the simple concept that came out of the International Water Association 15, 20 years ago, that leakage is composed in aggregate of individual events. And each leakage event has a flow rate and a duration that then produces a volume of loss. So the component analysis software models each instance of leakage for you such that you can appreciate the breakdown of the whole picture of leakage. So for background, to model your background leakage with the model, you'll have to provide it with your operating pressure, which you should already have from your audit, as well as infrastructure information, which you should have from your audit, things like your miles of main and your service connections. The software then has a background leakage allowance that you can adjust with some indication of your infrastructure's condition, If you think that this doesn't quite get it right and your system is older or suffering more background leakage, you can account for that with a code.
So it's you can do this in a very complex and detailed way. I mean, you can assess background leakage for a system through field measurements, but obviously nobody is really wanting to go there unless for research purposes, basically. So what we've done in this model, we said we have these technical allowances for background leakage, right? You see for mains, that's a technical allowance, for service connections and so on. And then just like with the unavoidable annual real losses, so that's our technical minimum. And then in the model, we're asking you, what's the average age of your system? Is it a new system with, an average less than 50 years? Then most likely background leakage is going to be at that minimum. If you're operating an older system, as we age, as the system ages, there's more of background leakage happening. So then you get a multiplier for that. So there are 3 selection criteria based on system age, to make it very simple for you guys, to say, okay, average age is 80 years, therefore I'm clicking on this button, and then it calculates the background leakage for your system.
In the world of reported and unreported leakage, either leakage that finds you or you go out to find it and you repair it accordingly, you'll want to work with your repair data. And right off the bat, repair data may not be perfectly suited or tracked for this purpose. Often people track repair information to appreciate the costs, both labor and materials, of attending to leakage. So that's okay. The component analysis is a chance to put that data to a slightly alternate purpose and see how it does. The model will request the count of leaks that you worked with in a given audit period. Important to note that it should be the same audit period as your water audit so that the volumes are all corresponding. So you want to report the number of leaks, the infrastructure type. Was this a leak on a main? Was it a leak on a service connection? Was it in a meter box? Did somebody share a hydrant? Those sorts of questions. You'll also want to report that leak's runtime from the moment it entered your database and somebody called it in and said, there's water running down the road. When you became aware of it to when you contained the flow. We're pretty agnostic to everything after flow containment. If you spend a couple of days paving, great. That doesn't really pertain to water loss. So we're looking about the time from awareness to containment. There's also a modeling option for the discovery time between when the leak first started and when you found out that it existed. If you haven't done very detailed research-like work, you'll likely work with the default assumptions in the model to account for the full duration of the leak. So for each event, you'll report the infrastructure, the size if it's a main or a service connection, the duration, and then you can either work with your own flow rates or some defaults in the software.
Who in the room feels that you have that data available?
A few, yeah.
A few, okay. I mean, typically what we see is that you all keep track of your repair activities, right? For lots of reasons. The only thing that we see then with what you have in your databases is geared more towards equipment and financial tracking, right? Than necessarily the time tracking of how long did this event run for. So you might have the start time, and then as Lucy said, when you close out the work order, that's the next timestamp. So you're really missing the timestamp when did I pinch down the valve to contain that leak, right? That's maybe not something that you record right now, which doesn't mean you cannot use that tool. Start out with assumptions, right? You know typically what you're aiming for. Typically when we are aware of a main leak, we repair it within 6 hours. I mean, you have the emergency ones that are out there anyway right away, but then the average main leak, for example, typically we repair it within a day, right? Service leak maybe within 2 days. Whatever it is, that's totally fine. You can work with those numbers as a starting point. And then again, use those guidelines, and we've also developed a spreadsheet here that you can use where you see all the data entries that you would need, or the data points that you would need in an ideal scenario. And you can see if you can incorporate those data points in your work order management system.
And if you find that when you ask for your repair data and it shows up and it gives you a count of events and maybe what sort of infrastructure was repaired, but falls short on some of these other factors, maybe over the next few years you work with your repair folks to figure out what is reasonable data to collect to inform this model. It's a pretty iterative process, so the first year you do it might be incomplete. Might be inaccurate, but it'll be educational nonetheless, and you can get better data moving forward.
And also on the flow rates, since you're assigning flow rates to each event, right? You have a 4-inch main break, for example. I mean, some of you make an estimation on site, some don't. If you don't do that, then you can use the model and use some industry flow rates, where simply it's multiplying duration by flow rate that calculates the volume. So that's not an issue if you don't do that. So now, since we have broken it down, it's really into the strategy development. What is the right strategy to get to our economic level of leakage? Reminding you guys the 3 tools: response time, pressure management, and leak detection. And with the model now, we move forward into the economics.
And so just to give you a preview of the afternoon, once we have lunch, which will be in this room, and we'll let the webinar folks go get lunch for an hour, we'll come back and we'll talk about designing a water loss control program. Now that we have the information to understand our system losses, we now want to figure out how we can deal with them and without incurring extra expense. After talking about water loss control program design and the tenets of that, we'll speak about our case studies. We have Tom in the room, whose system, Madison Water Utility, was one of our wonderful participants. We also worked with the City of Ann Arbor and learned some very interesting things about what water loss control looks like in the Great Lakes region, and took general methodology and applied it to specific circumstances, and got different results, which is kind of fun to think about. So we'll talk about that this afternoon. We'll also have Tom in the room to talk about lead service lines, and Mary Ann will speak a little bit more broadly to the national conversation on water distribution efficiency, and Denise Schmidt from the PSC in Wisconsin will speak about Wisconsin murmurings and how this fits into her organization's agenda for the state. Also time for questions, and Chelsea, our moderator, has some announcements, so I'm going to let her go at it.
We've gotten just a few questions from the people who are at-home viewers. The first is whether the presentation will be made available after today's workshop, and it will be posted to AWE's website, and everyone who's registered for the in-person workshop as well as the webinar will receive an email notice that it's available, so you can go back and watch any parts that really stuck out to you or review any information that you think would be useful to you. And then the other question that we received, if you don't mind repeating, that trick question from the quiz regarding customer bill adjustments. If you could just repeat that explanation.
The trick question from the quiz. People love trick questions, don't they? So the question is, when you have a customer billing adjustment, how do you deal with that in your water audit? Distinctly from how you deal with that in your customer relations and your finances, this is a different question. And so we're trying to figure out if the volume of water was billed or unbilled, or if it was a form of water loss. So, bless you, Reinhard. The question first is, what was adjusted? Were finances adjusted and the volume was left untouched? Or were finances and the volume adjusted, such that I do have to think about how that volumetrically affects my water audit? If the customer bill was adjusted downward, meaning that I have reduced the volume, and that volume was actually legitimate, it passed through the meter, it happened, we'll want to think about that as a form of either financial loss and allocate it to an unbilled volume so that it's non-revenue water, or if that volume that I docked off my bill is a form of apparent loss, meaning that it was lost in tracking. So I've adjusted the volume of my bill, but I don't actually know what the original volume of water that passed through was to begin with, and so it's gone missing in the paper shuffle. The question is, what do you know about it, and how does that affect your water audit? So you'll want to step through the process of adjusting that bill so that you can appreciate how it manifests in a volume and in revenue generation, whether it's non-revenue or revenue water. Does anyone in the room have any questions? Yeah. That's also welcome too, and you can also pull us aside over the lunch hour.
We've thrown a lot at you in short 2 hours, that's for sure, but yeah, any questions?
Could you touch on a little bit the 32 connections per monolith,
right,
who are the smaller systems that might be more spread out,
okay,
and performance indicators?
Sure. So in order, when we do this normalizing of this big volume of real losses or apparent losses, and typically divided by the number of service connections, We do that in order to compare apples with apples, right? But then if you have systems that are of a rural character, where you have less than 32 service connections per mile, we actually normalize per mile of main. So we divide the total volume of real losses by the miles of mains that they are operating. Reason being there is, I mean, that's also, for example, a good point why the infrastructure leakage index is actually really useful. So we had a couple of cases with rural systems where they were looking at their percentage loss and then connect real losses per connection per day, and they looked awful. In the context of the infrastructure leakage index, it gives you an allowance for all of those miles that you have to operate, and then it really reflects better your performance. If you're a rural system, you have lots of mains and a relatively small number of service connections and customers, right? So percentages are really not in your favor, and also normalizing per connection is not in your favor, but that's automatically done in the software anyway.
The other thing to think about in terms of performance indicators in certain systems, we have on the one hand the rural systems, and on the other hand the small systems, which may or may not be rural. And for the systems that are very small, at a service connection break of about 3,000 connections total, the infrastructure leakage index is no longer a useful performance indicator. When the systems are that small, the assumptions about how they leak are different, and so we don't use the IOI. It's not even calculated in the software. There are other ways, particularly this normalizing to length of mains or connections, that are more useful to think about leakage.
Any other questions?
Yes.
Sure.
When we're talking about main breaks,
Yep.
is there a
Standard.
so we develop a main break and it is found today. With our soil, that main could have been leaking for a day, a week, a month,
Right.
6 months. Is there a standard to say, okay, well, here's a parameter that you should use for these types of things for gallons of logs?
So a couple of answers there, I guess. One, so for failures that find you, typically what we've agreed on in the industry is to say, well, those that come to the surface are of a more severe nature than those that are running underground that you got to try and find. So the time to become aware of those leaks is assumed to be shorter. And there's some industry guidelines in the software and the report that goes along with it. So for a main break on an 8-inch main, it's probably not going to be weeks and weeks, but just a couple of days basically before this became a real issue. On the other end, for those folks that do leak detection, for example, right, the easiest scenario is you surveying the entire system once a year, right? You start on one end and end on the other end. So the assumption is that if you do the entire system once a year, on average, a leak that you found ran for half a year, because it could have developed right the day after you did the last survey, right, and you fixed it, or it just happened the day before. And so the average there is then half a year. So basically, if you do it twice a year, for example, the entire system, then it would be a quarter year. That's how that works. Want to throw out one more thing on failures, since what we've done also in the software model, since you're collecting all the failure data, right, and you're plugging it in, we've done some research to come up with standard industry numbers. So what is a typical failure frequency that you're experiencing in a system? And there are two guidelines, two numbers that we threw in there. One is industry average, and that has a significant grain of salt, that number, to it, because when we collected all of that data, right, we dug into all the research reports that are out there that talk about failure frequency, and the one thing that we found is, the industry is very consistent in how inconsistent they track their failure data. But anyway, it comes out at about 25 main failures per 100 miles per year. And then there was another study that's indicated that for an optimized system, you would say about 15 mains failures per 100 miles per year. So again, really interesting for you guys as you're plugging the data in there to see, is my failure frequency reflecting my leakage calculation also, you know? If you're calculating a lot of leakage for your system, then you would also assume that you have a lot of failures that already find you. You had a question back there.
I was just going to say, can you use your pumpage report for some of that loss that you're going to be reporting for your community rate? You know, 5-year averages the same month?
Well, can you repeat that?
Can you use your pumpage report
Yeah.
the same month for the last 5 years, do an average to see how much it increased between the reported failure
Right.
and what your average was for the last
Sure,
5 years? That would give you a better estimate on what you've lost.
If the event was big enough and so the year over year it's reliably comparable, right? I mean, there's other factors coming in, demands can be a factor. Maybe, I mean, I wouldn't be concerned to go into that detail. If you don't estimate your leak flow rate, just use the default values in there, and they're really, those are industry defaults. Use them. If over time you refine your estimations, that's great, but it's certainly not a must in order to use the model and figure out what's the breakdown between reported and unreported leakage volume.
So as we think about lunch, I know that lunch is provided for participants in the room. You also have the option, if you are so jazzed about water auditing that you never want it to stop, to work with an example scenario. We've got a piece of paper there by the door if you need one that talks about the Koala Water District and their audit period. I think it's a recent audit that they would like for you to compile. So to get the audit software, what you'll want to do is connect to the internet here. The code is up there. And
All capital letters.
all capital letters, there you go. And go to AWWA's water loss control webpage. Just a quick Google search will pop that up. There's an option to download the software. And what you have to do is tell them who you are and what your email address is so that they email it to you. The software committee is just tracking where people are downloading it, whether it's happening in Wisconsin or in, Papua New Guinea. That's helpful to know. So they'll take your email address and email you the Excel spreadsheet. You can download that. And then play around with Koala's example, and if you run across any questions, throw your hand up, and we'll put down our sandwich and come talk to you about water loss, because water loss is more important than sandwiches. So go for it, have some fun, and we'll rejoin the formal presentation in the webinar at
12:10.
12:10. There you have it, promptly. We're on a tight schedule here today, folks.